This is AP Calculus BC, and in this video I'm going to talk about section 5.6, which is about the fundamental theorem of calculus. So with the fundamental theorem of calculus, this is where we are going to start understanding how we can solve definite integrals using antiderivatives. And there's two parts to the fundamental theorem of calculus, and the first part is exactly that. It's going to allow us to understand how to use antiderivatives to solve these definite integrals. And you can see the first part of this is defined here at the beginning of these notes. We have the integral from a to b of f of x dx equals f of b minus f of a, where we have that capital F indicating that's the antiderivative function. But notice it says f is any antiderivative of that f function. So I'm going to explain what that means here in just a second by going through this example. So what we have here are two functions. And with these two functions, f of x and g of x, you can see there's a relationship between them. If I took the derivative of g of x, I would get f of x. If I took the antiderivative of f of x, I would have, at the end of it, I would have a plus 3x plus c. So you can see that g of x is one of the possible antiderivatives of f of x. So in terms of actually solving this out, I'm going to go through this in a couple of different ways. So the first thing I'm going to do is I'm going to use the fundamental theorem of calculus to solve this out. So the integral from 0 to 6 of 1/2 x squared minus 2x plus 3 dx. So that's what we're trying to solve. Now, what the fundamental theorem of calculus says I can do is I can take antiderivatives here and I can solve this. So that would make this 1/6 x cubed minus x squared plus 3x. Now, when we solve these definite integrals out, we are actually not going to be adding a plus c. And I'll explain why when we get to the second method of solving this out. But all I'm going to do is take my antiderivative without the plus c, and then I'm going to evaluate that from 0 to 6. Now, there's different ways that I can write this out. I like to bracket in my antiderivative and then show that the limits of integration 0 to 6 are going to apply to this antiderivative. And what the fundamental theorem of calculus said is that if I take this antiderivative and I plug in the upper limit, and then I subtract away the antiderivative with the lower limit plugged in, that'll give me the value of the integral. So that's what I'm going to do here. 1/6 times 6 cubed minus 6 squared plus 3 times 6. Okay, that's my antiderivative with the upper limit plugged in. And then with the lower limit plugged in, all of those terms are just going to give me 0. So in the end, this is going to simplify down. This will give me essentially 36 minus 36 plus 18. That's going to give me a value of 18. So the value of that integral is 18. That's one way that I can solve it. And if you think about that graphically, what's going on there is I'm getting the area underneath the f of x function, and we're going from 0 to 6. So that's going to give me a point about right here. And in terms of area, I'm looking at all of this area in here. Okay, so that's all the area that that integral would find. Now, there's another way we could solve this out, and this is where understanding what's going on with that plus c is going to make a little bit more sense. So the other way I can do this is I could say, okay, well, the integral from 0 to 6 of f of x dx, we established that g of x is one of the possible antiderivatives of f of x. So we could also say that it's g of 6 minus g of 0. And if I do it that way, look at what happens when we do this. So when we plug into the g of x function, I'm going to get 1/6 times 6 cubed minus 6 squared plus 3 times 6 minus 3/2. Okay, and then I'm going to subtract away g at 0. Well, if I plug 0 in, it's just going to give me negative 3/2. And notice what happened with the constant value of that function. I have a negative 3/2, I have a plus 3/2. So the constant value ended up canceling out. And that's always going to happen. Regardless of what that c value is, it's always going to cancel. So that's why when I did my antiderivative and I wrote plus 3x, I didn't do a plus c. because the plus c doesn't matter. And in the end here, I'm going to get the same result of 18. So there's a couple of things to get out of that. First of all, why do we use the fundamental theorem of calculus the way that we do? That shows you exactly the relationship. But the second thing that this tells us is also look at what the integral of f of x is actually representing. It's the net change in the g function. So if I were to look at this graph and look at the g function at 0 and look at the g function at 6, which would be way up here, if I were to subtract those two values, that's how much my function value has changed on that interval. It has changed by 18 units. Okay, so really two things that we can get out of that first part of the fundamental theorem of calculus. So let's just go through a couple of quick examples here of how this works, and I want to go through a little bit of notation. So this one, we have the integral from 3 to 6 of dx over x. So that's essentially 1 over x dx. So when we solve this out, remember 1 over x dx, I have the natural log of absolute value of x. I'm not going to write absolute value this time because I know that my limits of integration are all positive. So I really only need to deal with the absolute value, or excuse me, the natural log of just x, the positive part of absolute value function. So that means that my antiderivative here is natural log of x. I'm going to write my notation a little bit different way this time, just so you can see some different methods. One way you'll see this written sometimes is like this, with just a vertical bar and then a 3 to 6. And that's telling me natural log of x is going to be evaluated from 3 to 6. The reason I don't usually use this notation is because if there was more than one term, then you probably should have parentheses around it to make it really clear what the 3 and 6 are applying to. And for me, if I just put the brackets in, it's really clear that it's applying to all of the terms of the antiderivative. Another way you might see it written is just with a right-hand bracket like that. And again, kind of the same thing. The bad part about it is if you have multiple terms, then we'd be looking at, okay, we need to put parentheses in here to make sure we know which terms we're talking about. So for me, I usually just write it that way, and then it's really clear these limits of integration are going from 3 to 6. And it's applying to all of the terms in the brackets. So this would be natural log of 6 minus the natural log of 3, which I could write in a lot of different ways. But if I combine this together, that's the same as the natural log of 2. Okay, so these aren't necessarily difficult because all we're doing right now are basic antiderivative rules. So when you see these definite integrals for now, it's sort of like when we were doing the indefinite integrals, and you should be able to recognize basic antiderivatives just from knowing your derivative rules. Okay, so here's another example, negative 1 to 1, t squared minus 2 dt. Okay, so when you solve this out, antiderivative of t squared is t cubed over 3. Antiderivative of negative 2 would be minus 2t. And then I'm going to evaluate that from negative 1 to 1. Now, notice we have more than one term this time. The most common place that people make a mistake is not on the antiderivative. Where people tend to make a mistake is right here on this next step. So I'm going to plug 1 in. That's going to give me 1/3 minus 2. And then I have to subtract away the antiderivative with negative 1 plugged into it. If you actually write out this step and put in the parentheses like I'm doing, it will eliminate the chances of you making this mistake. So what I'm going to do here is plug negative 1 in. That's going to give me negative 1/3. And then negative 2t becomes plus 2. And now it's really clear that I am subtracting negative 1/3 and I am subtracting positive 2. Sometimes people try to skip this parentheses, the second set of parentheses that I have here, and the mistake they would make is they would write, okay, minus negative 1/3, and then write a plus 2 out to the right of that, but then forgetting that I need to subtract the positive 2. So you can really mess yourself up by trying to go too fast or leave little things out like that. So in the end here, I'm going to get negative 4 plus 2/3. So negative 4 would be negative 12/3, and that's going to give me in the end then negative 10/3. Okay, so again, not that difficult, but you just have to be a little bit careful about this in terms of how you write your solution out. All right, so let's take a look at this last one. And on the last one, we have a cosine function. So again, same idea. When we're solving this out, antiderivative of cosine is sine. I'm going to evaluate that from 0 to pi. And now it's just sine of pi minus sine of 0. Well, sine of pi minus sine of 0 is equal to, think about sine of pi is 0, sine of 0, 0. I'm going to get 0. And you can even then start thinking about these things graphically. What does the cosine function look like between 0 and pi? Well, between 0 and pi over 2, it's above the x-axis. Between pi over 2 and pi, it's below the x-axis. And those two areas, the area above and the area below the x-axis, are equal. So they essentially cancel each other out and give us a net result of 0. All right, so here's some things that you need to be careful with. On this next one, it says, what's wrong with the following calculation? So I want you to look at that, and I just want you to think about that for a second. So go through all of the steps and see if you can see anything wrong with that. Okay, so first of all, the antiderivative here is essentially negative 1 over x. That looks okay. It's being evaluated from negative 1 to 3. That looks okay. So you can see they did negative 1/3, and then when they plug the 3 in, I'm going to get minus, let's see, I'm going to plug the 3 in and get negative 1/3, and then plug the negative 1 in, and I'm going to get minus 1, so minus positive 1, and that gives me negative 4/3. So just on the surface, that looks okay. But then take a look at the graph of this, and think about what type of a feature this graph has at x is equal to 0. So this actually has a vertical asymptote within the limits of integration. So this is what we call an improper integral. And I mentioned this in the last section. And again, you're not really going to see this yet, but I want to present this to you now because every time you look at a definite integral, you should be thinking about the graph of the original function and whether or not the graph of the original function is continuous, and especially whether or not it has a vertical asymptote within the limits of integration. So always think about that before you jump into the problem and start solving it out. And that way, when we get to improper integrals in the second semester, you'll already have that as a habit. Okay, so one of the types of problems that you're going to see today is what we call writing our solution as an integral. So we're going to have a function defined by an integral. And they're telling you exactly what to do here. This is an integral that we really can't solve out. So what we're going to do is we're going to say, okay, our function is going to involve the integral of dy dx in this case. We know that dy dx is square root of 3 minus cosine x. We know y is 4 when x is negative 3. So let's say we want to find the y function. Well, again, we can't find the antiderivative. So what we do is we write our solution as an integral. And what we're going to do is we're going to write an integral and we're going to force our solution to go through the point negative 3, 4. Notice up here, this says our integral should be written in the form that it goes from a to x. So I'm going to leave that a out for a second, but also notice that it says f of t here. So f of t means I'm going to write my function in terms of t. And the reason we're doing that is t is what we call a dummy variable. It's essentially a placeholder. Because when I evaluate this thing, I'm going to plug x in for t. So I want to make sure that essentially that's what's happening there, is it's making it really clear that the x plugs in for the t. If I put an x over here where I have the cosine and I put dx, it's not necessarily wrong. It's just not really clear what's going on. So we usually use a dummy variable. So the last part of this is where I'm going to force this to go through the point negative 3, 4. And what I'm going to do is use the point that I know, the x coordinate that I know of negative 3, and I'm going to put that in as my lower limit. And the reason I'm doing that is because now if I evaluated y at negative 3, I'm going to get the integral that goes from negative 3 to negative 3, and that entire integral is going to give me 0. So knowing that to be the case, that means the last part of that then is plus 4. So you can see now we can check this. If I plug negative 3 in, do I get a y value of 4? The answer would be yes. If I take the derivative, will I get the original function? And we'll talk about this in a second, but yes, we will get the original function when we plug the x in for the t when we take the derivative. Okay, so I want you to try this next one and see if you can come up with the function written in terms of an integral. Okay, and here's what you should have come up with for that one. So y would be equal to the integral from 3 to x of tangent of t dt. And then I need to force it to go through the 0.35, so then out here I'm going to have a plus 5. Okay, so pretty simple to do. All right, so we also have questions like this in your assignment. Find the area inside the region. So this is just practicing with using the fundamental theorem and using those antiderivatives to solve these definite integrals out. But I'll just go through the setup for this. It's pretty clear we've got two separate functions that we're dealing with here. We're always above the x-axis. So all I have to do is integrate from 0 to 1, the square root of x function. And then for the second part of this, I would integrate from 1 to 2, and that would be the x squared function. And in the end, if we solve that out, you'll see you get an area of 3. Okay, so not really that difficult to do. Where you do want to be careful, though, on these area questions are questions like this next one. Finding area between the curve and the x-axis using antiderivatives. So we have y is equal to 4 minus x squared, and we're evaluating from 0 to 3. But remember, we're not just trying to solve an integral here. We're trying to find the total area between the curve and the x-axis. Okay, so we have to think about what this function looks like. And this is part of the reason I said always try to think about conceptually what's happening on these when you're solving them out. So 4 minus x squared would actually cross the x-axis at x is equal to 2. So I'm going to go up here and say 4 starts up here. And this is essentially what our graph would look like, right? So we've got that parabolic shape, but you can see that there's area above the x-axis and there's area below the x-axis. When I'm between 0 and 2, my area is above. When I'm between 2 and 3, the area is below. So I've actually got to break this apart into two pieces. I'm going to have an integral that goes from 0 to 2 of 4 minus x squared. And then I'm going to have another integral that goes from 2 to 3 of 4 minus x squared. Now, think about if I were to solve that integral from 2 to 3, is it going to give me a positive or a negative? Okay, and it's definitely going to give me a negative. So that means I've got to subtract that negative so that it will add the second area. And in the end, I'll end up with an area of 23 over 3. Okay, so that's if we were going to do this without a calculator. Now, if we had that same problem with the calculator, and where you'll see problems like this often is when they say, here's your velocity function, find the total distance traveled. Well, with a calculator, and I'm going to write that here just to make that really clear, this is with a calculator, we can make this into a one-step problem because we can force all of the function values to be positive. And remember, if you want to think about things that you did back in pre-cal, if you take the absolute value of a function, that is essentially taking all of the function values and making them measure a distance from 0. So all the function values become positive. What I can do then is I can say if I want the area with a calculator, I can just do one integral that goes from 0 to 3, and I can do the absolute value of 4 minus x squared. And that's going to give me the same result in one step. Again, keep in mind, we're not always going to have a calculator, but when you do have a calculator available to you and the question's talking about total area, you can just use an absolute value. You don't even have to worry about whether or not it crosses the x-axis. If you throw the absolute value in there, you're covered either way. All right, so the second part of the fundamental theorem of calculus is what we're going to talk about next. And the second part of the fundamental theorem of calculus is essentially establishing the fact that a derivative and an integral are inverse operations. So we have this relationship here where you can see that the uppercase f is essentially, we're saying that's the antiderivative function of the lowercase f function. Okay, so what this essentially says is that if I take the derivative of an integral, I'm going to get essentially what I started with. I'm undoing the operation that I'm doing. So it's like adding 2 and then subtracting 2, or multiplying by 10 and then dividing by 10. All right, so take a look at what's been done here. It says if I take the derivative of this integral from a to x of f of t dt, all I'm going to get is f of x. And I'll explain how this works by going through this first example. Now, there is a shortcut for this, but I'm going to show you the long way how this works first so that it's really clear what's happening. But the reality is these are really, really simple problems once you understand what's going on. So we're taking the derivative with respect to x of the integral from 4 to x of t cubed dt. So if I were to take the antiderivative here, what I would get is t to the fourth over 4. I'm going to evaluate that from 4 to x. And we're going to take the derivative with respect to x of whatever that is. Well, when I plug this in, my upper limit minus my lower limit, I'm taking the derivative with respect to x of x to the fourth over 4 minus 4 to the fourth over 4. And in the end, when I take that derivative of x to the fourth over 4 is just x cubed. Derivative of 4 to the fourth over 4 is 0. So all I get is x cubed. So essentially, all I've done is plug the x in for the t because I took the integral and then I took the derivative. I did inverse operations. Okay, so knowing that to be the case, when you see problems like this second one, the integral from negative pi to x of cosine t dt, I already know that this is just going to be cosine x because I know I'm going to take the antiderivative and then I'm just going to take the derivative. So really, really simple. Same thing on this next one. I've got 1 over 1 plus t squared from 2 to x. Well, that's just going to be 1 over 1 plus x squared because I'm just plugging the x in for the t. The only time we can't do it in such a simple way is if our limits of integration aren't just x's. So for example, if I have this next one, y is equal to the integral from 1 to x squared of cosine t dt. Well, now we've got to take the chain rule into account. And that's what's happening here is we're essentially saying, okay, let's use the same process, but keep in mind, we didn't have an x here. So we're going to rewrite y in terms of u, knowing that this is the substitution that we did. And now if I take the derivative of y with respect to u, I'm going to get the cosine of u. If I take the derivative of u with respect to x, I'm going to get 2x. And notice that these things are going to cancel out, giving me dy dx. So that's what we did down here. We got cosine u times du dx is cosine x squared times 2x, or 2x cosine x squared. So the main thing is you just have to take the derivative of that limit of integration into account when it's not just an x. Okay, so I'm going to show you a couple of examples here and then I'll have you try some. Okay, so we've got the derivative with respect to x, 2 to 5x of square root of 1 plus u squared over u du. So again, I know what's going to happen here. I know I'm going to plug the 5x in for the u. So that's going to give me the square root of 1 plus 5x squared over 5x. But then I just need to multiply by the derivative of 5x because it's not just an x. So I'm going to end up multiplying by 5. These 5s will cancel out. And in the end, I've got the square root of 1 plus 25x squared all over x. Okay, so not that difficult to do. Sometimes you're going to have limits of integration where the x is in the denominator. So just think about what would happen if you did the process here. 3t sine t dt. If I took the antiderivative, I would have to do the antiderivative at 5 minus the antiderivative at x. So there would be a negative involved. So since it's the lower limit, the process is still the same, but I would end up with a negative 3x sine x. Okay, so again, not that difficult to do if you're thinking about what's actually happening, taking the antiderivative and then taking the derivative. So there's 3 more of these that I want you to try. So I just want you to pause the video and take a couple of minutes and work through these 2, and then we'll talk about the solutions. Okay, so here are the solutions that you should have come up with. You can see the next one went from 3x squared to 10. So I'm going to end up with a negative because the x is the lower limit. And I'm also going to have to multiply by 6x after I've plugged in the 3x squared because that's the derivative of 3x squared. Now, the last 2 have x's in the upper limit and the lower limit. So again, if you think through the process here, it makes sense. I'm going to have 2 terms because when I do the antiderivative and then take the derivative, I'm not getting a derivative of 0 this time from a constant term like I was before. So essentially, I just have the upper limit minus the lower limit, but I've got to take the chain rule into account. You can see on this, this one with the x squared and the 2x, what I've got is I've got the derivative of x squared here. I've got the derivative of 2x there. Okay, so pretty simple. And then same thing at the end here with the integral that goes from sine x to cosine x. Same process. I did a little bit of simplifying, but essentially the same process there. All right, so the last question that I want to actually have you work through is this one. So this is a really common type of fundamental theorem of calculus question. And what it is a function defined by an integral. And I'm going to have you try this before I talk about the solution, just because I want you to see if you can understand how all this works. Now, what you're going to see with these problems is that it's really the fundamental theorem of calculus is the basis for how we're going to set this thing up. But the reality is, now that we understand that relationship, all of the other things that we did with applications of derivatives can start to come into play. So these questions tend to be kind of difficult for people because not only do you have to understand the fundamental theorem of calculus, but you also have to understand all of the derivative relationships and all the things about increasing, decreasing, and concave up and concave down, and understanding definite integrals and everything else. So these questions are kind of all-encompassing when it comes to basic understanding of derivatives and basic understanding of integrals. So notice we have h of x is the integral from 1 to x of f of t dt. What you're looking at here is the graph of the f of x function. So I want you to take a couple of minutes. I want you to pause the video, take a couple of minutes, try to work through all of the parts of this question. And when you unpause it, I will show you the solutions. Okay, so here's what you should have ended up with. And let me show you how I typically solve these problems. So first thing that I always do on these types of questions is I make sure I label my graph in terms of what function are we interested in here. So they said h is the integral of the f function. If I took the derivative of this integral, so right here, if I did h prime of x, that would be equal to f of x. So what I'm doing is I'm labeling this graph as h prime because I notice that all of the questions here are about h, the h function. Okay, so that's the first thing. Now, the first question says, what's h of 1? Well, all I have to do is substitute in, right? H of 1 is just the integral from 1 to 1 of f of t dt. Second question says, is h of 0 positive or negative, and why? Again, I just did substitution. H of 0 would be the integral from 1 to 0 of f of t dt. Remember that property that we talked about last time, which was I can switch my limits of integration and I can change the sign on the integral. So that's what I did here was I switched the limits and I made it the negative of the integral from 0 to 1 of f of t dt. Look at the integral from 0 to 1 of f of t dt. That would be this area right in here. So that's above the x-axis. That's a positive integral value, but we're taking the negative of that. That means h of 0 is going to be negative. All right, C, it says find the value of x for which h of x is a maximum. Well, they didn't say to justify, but remember, this is the graph of h prime essentially. So I need to know when does the derivative go from positive to negative. That happens here at x is equal to 4. So if I needed to justify my answer on this question, why is x equals 4 the maximum? Because that's where h prime of x switches from a positive value to a negative value. D, find the value of x for which h of x is a maximum, or excuse me, a minimum. So we've got a couple of things here. Notice that we've got included endpoints. So since we're including the endpoints, we have to consider what's happening with this function. So you can see with this function, I have positive h prime values. So I'm just going to draw a graph, sort of what this would look like. H of x goes up in value, and then it goes down in value. Now, then we have to think about, okay, understanding a definite integral and what it represents in terms of area, have we increased more or have we decreased more as a net result? So think of these two areas versus this big area. So which one seems larger? It seems like we've decreased more than we've increased as a net result. So that's what I'm going to use down here to say at x is 0, we'd have a local minimum. At x is equal to 8, we'd have an absolute minimum because we decreased all the way until we got to 8. And then E, it says find the x coordinates of all points of inflection of the graph of y equals h of x. So remember, we're looking at the graph of the derivative. If I have a point of inflection, that means my derivative went from decreasing to increasing or increasing to decreasing. So what I'm really looking for are these horizontal tangents. I've got one here, and one here. That's where the derivative changed direction from increasing to decreasing or decreasing to increasing. Okay, so there would be 3 points. And again, if I needed to justify, I could talk specifically at x is 1, the derivative went from decreasing to increasing. At 3, it went from increasing to decreasing, and so on. So they're not that difficult, provided that you've mastered everything leading up to this point. So what starts to happen here is if you didn't master everything back when we were talking about applications of derivatives, now your problems start to compound themselves, because not only do you have to understand that, but you also have to understand the fundamental theorem of calculus just to get to the point that you're going to use those derivative relationships that you should know. All right, so last thing that I have in here, I just wanted to show you some other rates of change. So the main thing is, I talked about the beginning that when we integrate a rate function, it's essentially telling me the net change in whatever that rate is measuring. So this is an example of that. Suppose that t hours after a pitcher of iced tea is removed from a refrigerator, its temperature is rising at this rate. 15 e to the negative t over 2 degrees Fahrenheit per hour. To the nearest degree, what will be the change in temperature of the tea 2 hours after its removal from the refrigerator? Okay, so this is pretty straightforward. If I want to know the change in temperature, I'm just going to write this as the change. It's going to be equal to the integral, and we're talking about time is 0 starting when we take this out of the refrigerator. So we're going from 0 to 2, that's the 2 hours, and it would just be 15 e to the negative t over 2 dt. And then we could solve that out. For now, this would be a calculator question. Eventually, we'll be able to solve this out. But that's all we would have to do. Now, there's a couple things you can do to make sure that you're doing things correctly. Think about the units here. This 15e to the negative t over 2 is in degrees Fahrenheit per hour. Then we're multiplying by dt. So I'm multiplying degrees Fahrenheit per hour times time, or times hours. The hours would cancel. I get a net result of degrees Fahrenheit, which is the change in the degrees. Okay, so that's one way you could write this integral out. One thing that I highly encourage you to do, if your function is already defined and it's a calculator question, rather than writing out a function, because a lot of times these functions are going to be really messy, I could also just write this as r of t dt. And that would actually be my preferred way for you to write a solution for this type of a problem, because it's just a little bit more concise. R of t has already been defined in the problem, so now I've got a really simple, clean integral that I can use as my solution. All right, the next page here, I just wanted to show you that there are a lot of, now that we've gone through fundamental theorem of calculus, there's a lot of AP free response type of questions that you might see. So the first type is actually this type of question, where you have a function defined by an integral. This is very, very common as being an AP free response type of question. And as we went through that, you could see why. There's so many things you have to understand to solve this question. It's a good way to assess your knowledge of calculus in general by giving you a function defined by an integral. In addition to that, we have this question. And in this question, you're given rate functions. And they ask you a bunch of questions about these rate functions. But if you notice in here, some of the things they ask you for, you have to understand that integrating the rate function is going to give you the net change like we just talked about, but they're also talking about an absolute minimum. Remember, we talked about that whole idea with the candidates test. They're also talking about writing a solution as an integral. So there's a lot of things that can come into play now that we've gone through the fundamental theorem of calculus. So I want you to read through this AP free response question on your own, but pay particular attention to the way that these things are graded. Notice the way the points are awarded. These are always 9-point questions, but I want you to really look at what are they awarding points for? What kind of things are they looking for? And the main idea typically is that we're really not looking at algebra skills. We're looking at, do you have an overall understanding of the process that's involved from a calculus perspective? All right, so at the end of these notes, I did attach a worksheet. And the purpose of this worksheet is to give you a little bit more variety in terms of the fundamental theorem of calculus questions that you might see, not just in Wiley Plus for homework, but also on your quizzes and on your tests and on the AP exam. So this worksheet is not something you have to do, but this one I would highly encourage you to work through some of these questions even after you finished Wiley Plus, because this is going to give you a better feel for what the questions will look like, especially on your tests at the end of this unit and on your AP test at the end of the year. So I do have all of the solutions for the worksheet here on the last page, so you can check your answers. But I anticipate there will be some questions on this worksheet, and we'll probably go through some of these next time in class.